It's the final chapter of this semester. We're going to talk about theories of covalent bonding. So in this chapter, the only types of compounds we're going to talk about are molecules. Those are ones that have covalent bonding. And this is going to be an extension of chapter 10. So if you're unfamiliar with chapter 10, please be sure to review it before starting this chapter. There's a few things from chapters 7 and 8 that you need to recall that will be directly applicable to chapter 11, and that's quantum numbers and the orbitals. A couple of things to remember. 2 electrons can occupy a single orbital, and if there are 2 electrons in an orbital, they're going to have opposite spins of one another. There are 4 different types of orbitals, and we classify them based on their shape. Remember, we have s orbitals, p orbitals, d orbitals, and f orbitals. In valence bond theory, we're going to talk exclusively about covalent bonding, which involves the sharing of electrons. And so we need to look at what is actually going on with those sharing of electrons. In chapter 8, we talk about electron configurations and atomic orbitals, and those are fine for an atom when it's all by itself. However, the orbitals are going to change a little bit when the atom undergoes covalent bonding. We know that a covalent bond is going to form when the orbitals of 2 atoms overlap with one another, and then the pair of electrons that they're sharing with each other is going to occupy that overlapping region. And we can put a maximum of 2 electrons in the overlapping orbital region. And these electrons also have to have opposite spin. Here's a crude depiction of a hydrogen molecule where each of those circles represents the 1s atomic orbital overlapping with the 1s atomic orbital of another hydrogen atom. And the 1 electron that comes from each of the atoms is going to go into that shared space, and that's going to form the covalent bond between each of the hydrogen atoms. And with these orbitals, when they overlap with one another, the extent of the orbital overlap is going to indicate how strong the bond is. Essentially, the more overlap there is, the stronger the bond can be. And the things that influence the orbital overlap are the orbital shape and the direction in which the orbital overlap occurs. A hydrogen atom's electron configuration is 1s1, and so each hydrogen atom is going to contribute 1 electron to the covalent bond in the hydrogen molecule. The 1s orbital from each of the atoms is going to overlap, and both electrons are going to go into that shared space where one is up and one is down, or one is clockwise, one is counterclockwise. This can happen with any of the atomic orbitals, and we're actually going to find out in the next few slides that the orbitals, as these atoms get larger, the orbitals are not going to retain the original atomic orbital shape that they have, the s, the p, and the d orbital shapes. They can actually change their shapes. But overall, when there is a bond between 2 atoms, a covalent bond, there's orbital overlap, and the 2 electrons that are shared between those atoms occupy that overlapping space. One thing to keep in mind, the greater the overlap of the orbitals, the stronger the bond, and the shape and the size is going to influence that greatly. And so atoms know that the atomic orbitals are not already in the optimal shape for sharing, and so what actually ends up happening is orbital hybridization. And so the atomic orbitals are actually going to combine with one another, or hybridize, in order to make these hybrid orbitals. So an atomic orbital, which is what we talked about in chapter 8, s, p, d, and f, they're going to change their shape into hybrid orbitals when they undergo covalent bonding with another atom. If you have an s orbital on an energy level and a p orbital on an energy level, and they mix together, they're going to make a hybrid orbital, which we call sp. So here's an example of a 2s orbital and a 2p orbital. When they mix together, they're going to change their shape, so these would represent the hybrid orbitals. And this shape is now going to allow for the maximum amount of overlap with another atom, and that's the reason that atoms make hybridized orbitals. So let's look at all the different types of hybrid orbitals and how many you get when you mix them together. So I'll start here in the middle. The type of hybrid orbital that forms depends on the type of orbitals that are mixed together. If an s orbital and a p orbital and another p orbital combine together, we get what's called an sp2 hybrid orbital. And so the name of it directly shows you what orbitals were combined. We have an s and 2 p's. And the correct way to demonstrate that is sp2, where the 2 is superscripted. The number of hybrid orbitals that is formed equals the number of atomic orbitals that was mixed together. So if we have a situation where we combine an s orbital and a p orbital, and they're on the same energy level, we have 1 plus 1, we get a total of 2 sp hybridized orbitals. The shape and orientation of a hybrid orbital is going to help to maximize the overlap with the hybrid orbitals from another atom to form the bond. So essentially, the whole purpose of these hybrid orbitals is to maximize overlap to strengthen bonds. And there are 5 different types of hybrid orbitals. We have sp, sp2, sp3, and remember there are only 3 p orbitals on any sublevel. The next one would be to add d, sp3d, sp3d2. So these are the only 5 types of hybrid orbitals that exist. And one convenient thing about these hybrid orbitals is if you know the electron group arrangement around a central atom, you can very easily predict the type of hybrid orbitals that are present. If the atom has linear electron group arrangement, it has sp hybridized orbitals. If it's trigonal planar arrangement, it's got sp2 hybridized orbitals. If it's tetrahedral, sp3, trigonal bipyramidal has sp3d, and octahedral has sp3d2. And the way I like to remember it is the letters that I need to write down correspond to the number of electron groups. For instance, linear has 2 electron groups, so I write down 2 letters, S and P. Trigonal planar has 3 electron groups, so I have to write down 3 letters. And the only way I can do that is sp2. Tetrahedral has 4 electron groups. There are 4 letters. 5 electron groups, 5 letters, 6 electron groups, 6 letters. Here's that information organized in another way, where I have it vertical. These are your different types of hybrid orbitals. These are the electron group arrangements that they correspond to, and for those of you who liked that ax notation, I have put it on here. Remember, you don't need to know the ax notation if you don't want to. And then finally, I have the atomic orbitals that overlap and the resulting hybrid orbitals that you get. And so there's a little key up here to evaluate what I've written down. And so if you combine an s orbital and a p atomic orbital, you get a total of 2 sp hybridized orbitals. If an s and 2 p orbitals are combined, we get a total of 3 sp2 hybridized orbitals. We're going to look at the different types of hybrid orbitals individually and also look at examples of molecules that have these types of hybrid orbitals in them. We're also going to revisit the concept of orbital diagrams and show how we can modify those orbital diagrams. Remember those atomic orbital diagrams from chapter 8? We can modify those to represent the hybridized orbital diagrams. So the first type of hybrid orbital is sp hybrid orbital. Remember, any atom that has a linear electron group arrangement has sp hybrid orbitals in it. And sp hybrid orbitals are made when an s atomic orbital and a p atomic orbital are combined, and we get a total of 2 sp hybridized orbitals. And so this beryllium dichloride molecule right here is an example of an atom that is going to have sp hybridized orbitals. And you would be able to predict that because you would predict that beryllium has 2 groups of electrons around it, so it has linear electron group arrangement, meaning it's going to have sp hybridized orbitals. And if we look at the atomic orbitals, so these are the atomic orbital from chapter 8, where beryllium has 2 valence electrons, and those 2 valence electrons are in the 2s atomic orbital. And so when beryllium goes to make the molecule, what it does is it takes that 2s orbital and one of the 2p orbitals to make a total of 2 sp hybridized orbitals. And then it takes those 2 valence electrons and distributes them into the hybridized orbitals. We also have these 2 unhybridized orbitals, which can result in double bonding, which we'll talk about a little bit later in the chapter. But each of these hybrid orbitals has space for 1 more electron, and that represents where the bonding is going to occur. And so the chlorine atom is going to come in and fill that space with its electron. And so each of these partially filled hybridized orbitals represent a single bond that can occur between that atom. The next type of hybrid orbital is sp2. We have an s and 2p atomic orbitals to make a total of 3 sp2 hybrid orbitals. Boron is an example of an atom that often has trigonal planar electron group arrangement, And if it has trigonal planar electron group arrangement, that means it has sp2 hybridized orbitals present. And so in a boron atom, all by itself, it hasn't bonded to anything yet. It has 3 valence electrons because it's in group 3a. Has 2 of those electrons in the 2s orbital and 1 in the 2p orbital. And when boron goes to make a molecule such as Bf3 shown here, it takes the 2s orbital and 2 of the 2p orbitals, combines them or hybridizes them to make a total of 3 sp2 hybridized orbitals. And then it takes those 1, 2, 3 valence electrons and puts 1 into each of the hybrid orbitals. And now each of these empty spaces here represents a point where boron can form a single bond to another atom, like it is shown here in Bf3. The fluorine atom comes in and fills that space by sharing one of its valence electrons with boron. And so here's a depiction of this molecule where boron has these sp2 hybridized orbitals. One of the electrons is from the boron atom. The other electron comes from the 2p sublevel of fluorine. sp3 hybrid orbitals are very common in organic chemistry, and we're going to go over 3 different atoms that have sp3 hybrid orbitals in them: carbon, nitrogen, and oxygen. Those aren't the only atoms that can make these types of hybrid orbitals, but they're the ones that are really common. Recall, sp3 hybrid orbitals, you combine an s and all 3 of the p orbitals on a sublevel to make a total of 4 sp3 hybridized orbitals. Any atom that has tetrahedral electron group arrangement also has sp3 hybridized orbitals in it. Carbon is an example of an atom that commonly has tetrahedral electron group arrangement. If you have a carbon atom and you're drawing the orbital diagram all by itself, so this is just the valence electrons, carbon has 4 valence electrons, 2 in the 2s orbital and 1, 2 in the 2p sublevel. When carbon goes to make bonds, if it's going to make the molecule CH4, this is methane, it's going to combine the 2s orbital and all 3 of those 2p orbitals to make 4 sp3 hybrid orbitals. And it'll take those 4 valence electrons and distribute them evenly throughout the hybridized orbitals, 1, 2, 3, 4. And so each of these has an empty space available for carbon to form a single bond to another atom, such as it is here in methane. The sp3 hybrid orbitals overlapping with the 1s orbital of the hydrogen atom, and then we have the shared pair of electrons between those 2 atoms to make the single bond between them. Next we'll look at nitrogen. It's also going to take its 2s sublevel and the entire 2p sublevel, and it's going to mix those together to make the hybridized sp3 orbitals, so 4 of them total. But nitrogen has 5 valence electrons, 1, 2, 3, 4, 5. And if it's going to distribute those 5 valence electrons into the 4 hybridized orbitals, one of those orbitals has to be completely filled with electrons, and the other 3 will only have 1 electron. And that completely filled hybrid orbital that has 2 electrons in it represents the lone pair of electrons that we so commonly find on nitrogen atoms. Those 3 partially filled orbitals represent points where nitrogen can make single bonds to other atoms, like it is in the ammonia molecule here. And so here we have this sp3 hybrid orbital. This one represents the one that is completely filled with nitrogen's valence electrons, so this one right here. These 3 that come out and bond to a hydrogen atom represent this one, and this one. Next, we'll talk about oxygen and its sp3 hybridized orbitals. Like carbon and nitrogen in the last 2 examples, oxygen will often have tetrahedral electron group arrangement. Again, it doesn't exclusively have it, but in many cases it does. It'll combine its 2s and 3 2p atomic orbitals to make a total of 4 sp3 hybrid orbitals. That's the same as the carbon and the nitrogen example. But an oxygen atom has 6 valence electrons, and so if it distributes its 6 valence electrons properly into the hybridized orbitals, we get 1, 2, 3, 4, 5, 6. 2 of the hybrid orbitals are completely filled with electrons, and those represent the lone pairs that you find on oxygen. 2 of the hybrid orbitals only have 1 electron, and those represent regions where oxygen can form a single bond to another atom, like it is in the water molecule. You're not going to have to be able to draw a hybridized orbital diagram, but you should be able to interpret a hybridized orbital diagram. And so if I were to show you this picture of the orbital diagram here, you should be able to predict how many lone pairs you would expect that atom to have and how many single bonds you would expect that atom to have. Let's move on to orbitals that have, hybrid orbitals that have a d sublevel incorporated into them. And remember, we talked about in chapter 10, the types of atoms that are capable of having an expanded valence are the ones that are in period 3 and higher. And the reason the atoms can have an expanded valence, so more than 8 electrons, is because they have an empty d orbital available to borrow. And so here I'm actually going to show you it borrowing the d orbital. And so phosphorus is an example of one of the atoms that can have an expanded valence. In the example here of PCl5, it's got trigonal bipyramidal electron group arrangement, so we know it has sp3 hybridized orbitals, and it has a total of 5 of them because it combined 5 atomic orbitals to make those. And so here's the valence electron configuration for an isolated phosphorus atom. Remember that 3d sublevel is completely empty, but phosphorus is capable of borrowing one of those empty orbitals when it hybridizes. And so it's going to take its 3s, all 3 of the 3p orbitals, and one of those empty 3ds to make a total of 5 sp3d hybridized orbitals. Phosphorus has 5 valence electrons, and so if it distributes its valence electrons, the 5 valence electrons, into the 5 hybridized orbitals, there's 1 electron in each of the orbitals, meaning phosphorus can now make a single bond to 5 different elements like it does here in PCl5. Finally, sp3d2. All of these atomic orbitals get combined to make a total of 6 sp3d2 hybridized orbitals. Atoms that have octahedral electron group arrangement have these types of hybrid orbitals. One example of a molecule that has octahedral electron group arrangement is SF6. Remember, sulfur is in period 3, so it is capable of having an expanded valence. And so here on the left we have the atomic orbital diagram for a sulfur atom. 2 electrons in the 3s sublevel, a total of 4 in the 3p sublevel. When it makes the hybridized orbitals, it combines all of these atomic orbitals to make a total of 6 sp3d2 hybrid orbitals. Sulfur has 6 valence electrons, and so if we distribute the electrons into those 6 hybridized orbitals, we get 1 electron in each, meaning the sulfur atom in this case can form a single bond with 6 different elements. So let's do an example. I have some molecules drawn here, and what I want you to do is first identify the electron group arrangement and then the type of hybrid orbitals that you're going to find, or the orbital hybridization you would expect. Remember, we talked about the orbital hybridization is directly related to the electron group arrangement, so that's why I'm having you identify that first. In the molecule PCl5, we have 1, 2, 3, 4, 5 groups of electrons. The name of that electron group arrangement is trigonal bipyramidal. And if you have trigonal bipyramidal arrangement, the type of hybrid orbital that corresponds to that is sp3d. Remember, you need to write down 5 letters, or that's my quick trick for remembering that. I've got 1 S, 3 P's, and a D. If you total those up, there's 5 letters there. The next example, chloroform. We've got carbon in the center here. We've got 1, 2, 3, 4 groups of electrons around it. And so if there are 4 groups of electrons, that corresponds to tetrahedral electron group arrangement. And when there's tetrahedral electron group arrangement, the type of hybrid orbitals you would expect are sp3. For carbon here, here's an example of carbon where it does not have tetrahedral electron group arrangement. And I'll talk a little bit later about how the hybrid orbitals correspond to the formation of double and triple bonds. But here we're still going to go off the basis of the electron group arrangement. There's 1, 2 regions of electrons. So that corresponds to linear electron group arrangement. And anything that has linear electron group arrangement has sp hybridized orbitals. The last example, BF3, it's trigonal planar because there's 3 groups of electrons. And anything with trigonal planar arrangement has sp2 hybridized orbitals. The final topic in chapter 11 are the types of covalent bonds. And so now we'll start talking about the single bonds versus double and triple bonds. And we can classify a covalent bond based on the type of overlap that exists between either the hybrid orbitals or the atomic orbitals. We have sigma bonds and pi bonds. Sigma bonds are represented with the lowercase Greek letter sigma, which is this little letter right here, and then pi bonds are represented with the lowercase Greek letter for pi. Sigma bonds result when there is end-to-end overlap of the orbitals. So one example of that here is these two carbon atoms. There is direct end-to-end, so the tips of the orbitals are overlapping with one another, and this represents a sigma bond. All single bonds are going to be considered sigma bonds. There's end-to-end overlap of the orbitals. Pi bonds occur when you have double and triple bonds. So anytime you have a double or triple bond, you have at least one pi bond present. Pi bonds are formed by a side-to-side overlap of unhybridized p orbitals. So in some of the examples I showed you, some of the p orbitals were used for hybridization, and some of the p orbitals were left unhybridized. And those unhybridized p orbitals are the ones that are capable of participating in double and triple bonding. Anytime you have a double bond, there is one sigma bond in it and one pi bond. So there's one set of end-to-end overlap and one set of side-to-side overlap. So here we have an unhybridized p orbital in this carbon atom, and it's hard to stretch those out. I have better pictures on later slides, but there's side-to-side overlap of those p orbitals. Pi bonds are going to be weaker than sigma bonds because remember, the extent of the overlap directly influences the strength of the bond. If you have end-to-end overlap of the bonds, it's going to be stronger than if you have just side-to-side overlap. There's not as much overlapping occurring. We'll look at a couple of different organic compounds. We're going to look at ethane, ethene, and ethyne, and the major difference between those is one of those has a single bond between the two carbons. Ethene has a double bond between the two carbons, and ethyne has a triple bond between the two carbons. And so if we have this ethane molecule, there's a single bond between the two carbon atoms. And remember, a single bond is a sigma bond. The nice part about that is it's easy to remember because they sound the same. And so we have a sigma bond right here. Each of these carbon atoms has 4 groups of electrons around it, 1, 2, 3, 4. So it has tetrahedral electron group arrangement, meaning each of these carbons has 4 sp3 hybridized orbitals. And so each of those sp3 hybridized orbitals is used to make a bond to another atom. And so the sp3 hybridized orbitals here between the two carbon atoms have direct end-to-end overlap, which represents the sigma bond. Each of these bonds between carbon and hydrogen also represent sigma bonds. The next example is ethene, where there's a double bond between the two carbon atoms. That double bond between the two carbon atoms represents one sigma bond and one pi bond. Each of the carbon atoms has 3 groups of electrons around it, meaning it has sp2 hybridized orbitals, and it's got 3 of them. And so each of the 3 sp2 hybridized orbitals is used to make a sigma bond between the carbon and the hydrogen here, and the 2 carbon atoms. And if only 2 of the p orbitals are used for hybridization, that means that there is an unhybridized p orbital available. And this unhybridized p orbital is where the pi bond is going to form. And so here we've made this p orbital a little bit bubblier to show how it can overlap side to side with the 2p orbital of another atom. So each of these carbons has an unhybridized 2p orbital, and so there can be a pair of electrons being shared between these 2p orbitals. And so we get direct end-to-end overlap here, which is the sigma bond, and side-to-side overlap here where there's a pair of electrons forming that one pi bond. The last example is ethyne, where there is a triple bond between the 2 carbon atoms. Each of the carbon atoms has sp hybridized orbitals because it's linear electron group arrangement. It's got a total of 2 sp hybrid orbitals. Each of the sp hybrid orbitals is used to make a single bond. So one of the single bonds goes to hydrogen, one of them goes to the other carbon. And so there's one sigma bond between the 2 carbon atoms. And if only one of the p orbitals is used for hybridization, that means that there are 2 unhybridized p orbitals available. So one of them is here in black, the other one is here in red. And those orbitals can overlap side to side between these two carbon atoms. Here it is blown up to show the overlap a little bit more substantially. And there's a pair of electrons here in this region, a pair of electrons here in this red region, and then the pair of electrons from the sigma bond in between the two carbon atoms. And so that represents the triple bond. And any triple bond has one sigma bond in it and two pi bonds. One important concept about these sigma and pi bonds, sigma bonds can rotate freely around the bond axis if there's no pi bond present. However, as soon as you introduce a double or a triple bond, or a pi bond in general, the pi bond makes it so that the molecule cannot rotate freely around that bond axis. And so the carbon and hydrogen bond here, that's a sigma bond. That hydrogen can rotate freely around the axis. But between these two carbon atoms, it cannot rotate freely. And that gives rise to something that we call isomers, where we have two compounds with the same molecular formula, but the way the atoms are arranged in three-dimensional space is different, and it makes the chemical and physical properties different. For example, both of these molecules have the chemical formula C2H2Cl2, and they're both called dichloroethene. However, one of them has both of the chlorines on the same side, so on the bottom side of the molecule, and the other version, the trans version, has the chlorines on opposite sides. And these two compounds actually have different chemical and physical properties, such as different melting points and different boiling points. This is a concept that will get explored much more in detail if you move on to organic chemistry. Here's an example where I'm giving you an organic compound. So these molecules are a little bit more complex than the Lewis structures you're used to drawing, but you should be able to look at this molecule and identify the orbital hybridization around each central atom, and then also figure out how many sigma bonds and pi bonds are in the entire molecule. So first, let's go through and identify the orbital hybridization on each of these central atoms, each of these three carbon atoms. And remember, you can do that if you know the electron group arrangement. So you have 1, 2, 3, 4 regions of electrons, which is tetrahedral, and that corresponds to sp3 hybridization. This carbon also has 1, 2, 3, 4 regions of electrons, so it will also have sp3 hybridization. This carbon has 1, 2 regions of electrons, linear electron group arrangement, and so the orbital hybridization that corresponds to that is sp. Finally, we need to count our pi bonds and sigma bonds. So each single bond represents one sigma bond. And then you have to remember how many sigma and pi bonds you have in a triple bond. In any triple bond, there's one sigma and two pi bonds. So we can highlight all of the sigmas, 1, 2, 3, 4, 5, 6, 7, 8. And then these other two in the triple bond represent the two pi bonds that are present. In this molecule right here, we have 2 regions of electrons, so it's sp hybridization. This carbon right here is identical, so it's also sp hybridization. And then we need to count up our sigma and pi bonds. Each of these single bonds counts as a sigma, and then one of the bonds in the triple bond is a sigma. So we have a total of 3 sigma bonds, and the other 2 bonds in the triple bond are pi bonds, side-to-side overlap. This final example, this represents a molecule of acetic acid. We have 1, 2, 3 central atoms that we need to identify the orbital hybridization. This carbon has 1, 2, 3, 4 regions of electrons, so it's sp3. This carbon has 1, 2, 3 regions of electrons, so the orbital hybridization is sp2. And then this one often gets misidentified. Some students want to identify it as linear because you're just looking at the bonds, but remember when we're looking at electron group arrangement, we count the lone pairs as well. So we have 1, 2, 3, 4 regions of electrons, and that would correspond to sp3 hybridization. And we'll count up our sigma and pi bonds. Each single counts as a sigma, and then in a double bond, one of those bonds is a sigma bond, and the other one is a pi bond. So we have a total of 7 sigma bonds in this molecule and 1 pi bond. Another ALEKS example has you identifying the hybridization in small molecules. And in these examples, you're going to need to draw the Lewis structure for the molecule or the ion that is provided before you can identify the hybridization. So you'll have to remember your Lewis structure drawing rules. In this first example, we have PBr4 with a negative charge, and so if you follow the rules, you should end up with a molecule that looks something like this. You have to draw it so that phosphorus has an expanded valence. That's the only way that you'll get the correct Lewis structure. I would recommend that you identify the electron group arrangement first and then identify the orbital hybridization from there. If you can directly go to orbital hybridization, that's fine, but I like to go through arrangement as a reminder. We have 1, 2, 3, 4, 5 groups of electrons. That's trigonal bipyramidal. And the hybridization that corresponds to that is sp3d. And I believe in this example, they just give you an empty box and you have to type in the hybridization yourself. And so the thing you would want to type in is this sp3 with a 3 superscripted d. The second example involves the perchlorate anion. So if you draw the Lewis structure for the perchlorate anion correctly, you have chlorine in the center with the surrounding oxygens. Chlorine does not need an expanded valence in this case. If we identify the arrangement, we have 1, 2, 3, 4 regions of electrons. That corresponds to tetrahedral electron group arrangement. And the hybridization that goes with tetrahedral is always sp3 hybridization. And so the answer for this one, I believe you would draw right in sp with a superscripted. And that's the end of chapter 11 and also the end of the semester. And so I hope it wasn't as terrible as you expected. And I wish you all the best of luck on the final exam and in your future endeavors.